we will go now into k-nearest neighbors, which I think we'll have enough time to kind of go into a little bit. It's an unsupervised learning algorithm. So this is actually section 33. So note that it's before decision trees, and at least on the curriculum. So I'm going to go ahead and share my screen again. I realize that's probably just, I should have just not closed it. There we go. Okay, so k-nearest neighbors is an unsupervised learning algorithm. I don't think we're going to go through the whole thing. I realize we only have about 20 minutes, but that should be enough to get most of it through here. So k-nearest neighbors is a pretty cool algorithm. It's an unsupervised learning algorithm, which means you don't actually need to know what the different targets should be. So there's a lot, it's really useful in this way to like find, what's it called? Like find things that, find different groups. That's really what unsupervised learning really is a clustering algorithm. But before we do that, we need to know basically, because we're doing clusters, that's kind of like how our description of saying these things are a group. If they're closer together, then we can say they are similar to each other. And since we don't actually have like a target of, we don't have a feature that is a target, right? We don't know actually what group they belong to. This is the only way, well, this is one of the ways we can say, oh, these groups belong together. So we have some different distance metrics. So it turns out it's not as simple as just saying, oh, if they're close together, because there's a lot of ways you can say what is close together. And so this is where we have, for example, the Manhattan distance. So we'll actually go through Manhattan, Euclidean, and Minkowski, which are basically just like, Minkowski is kind of like a general form of these other two. Euclidean distance is what you'll probably be most familiar with, but Manhattan distance is pretty simple. Basically, it's your walking distance. So if you imagine you have 2 points, this black dot here, this black dot here. Basically, you say, how far away are they from each other? You can basically do a couple things, right? One is that you can just like literally cut across like this, right? This is actually what you normally would do, say, oh, as far as the crow flies, right? It's saying how far something is. But if you imagine you're like on city blocks, what you could do is just say, okay, you could say it's technically, 2 miles away, but it's not actually 2 miles away because that's as far as the crow flies. Basically, if you were a bird, you just fly right over to it, right? It's like, well, we're not a bird. So what you could do is like, well, you could write, basically, if you're like in a nice, beautiful block system like this, you could just walk up, so many units. So let's say 1, 2, 3, 4, 5, 6 blocks. And then you walk off to the right, 1, 2, 3, 4, 5, 6 blocks. So you've walked a total of 12 blocks total. It's 12 blocks away. And that's kind of more realistic in what's going on. Now you might ask, well, what if I take like a bunch of zigzaggies kind of stuff going through here? Would that be faster? Well, we can count this out real quick. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Turns out it's the same distance. No matter where you are, as long as you walk those blocks, this will always be 12 blocks away. And this is the Manhattan distance. Basically, it's the very simple way of saying how far would it, like walking distance would you be without having to cut through buildings and such. And so it's a really basic formula. Basically, it's saying this absolute value between A and B. It's saying how far to the left, like you can imagine rise or run, how far to the left, how far off to the right. And that will give you the actual distance for Manhattan distance. If you were trying to code this, I think I imported the part, yeah. You can see here, if I have a multidimensional, so notice this is 3 dimensions. This is 1 point right here, point A. And this is at point 2, 3, 5, and the other one's at like 1, -1, 3. And you say, okay, how far away are these together? You basically just have to go for each part, say how far to go from 2 to 1, how far to go to 3 to -3, how far to go to 5 to 3, and then add those together. So you can see here, if I do this real quickly, you can see here the differences. Basically, just take the difference between each part. Because remember, NumPy will just subtract 2 - 1, 3 - 1, and so on. And you can see here, it gives me 1, 4, 2, just the difference between these parts, right? So this is basically the distance in each part. And then we say, okay, we want the absolute difference right here. So we want to make sure there's no negatives. So if I switch B and A, that would be an issue. But you can see here, you're not going to have an issue. If I did switch B, might say, you'll see it's like, oh, there's negative. Well, we just do the absolute part, and then it's fine. And then we just sum this part. So we just 1 + 4 + 2. So that should be 7, right? So it's a distance of 7. So that's essentially how you would essentially code what this would be here. Relatively simple, pretty straightforward, right? How's it sound? Make sense to you? Yeah. The main thing is basically, if I did for 2 dimensions, basically I'm just saying how far is it up from here and how far is it to the left over here. And in 3 dimensions, I have also how far in the 3rd direction. If I had 4D, you would just basically, how far is it from this direction? How far is it from this direction? How far is it from this direction? And then however far 4D is. But basically, it's just saying how far you're going each block. And that's why we can just simply subtract these two right here. Okay. So yeah, this is kind of like the simplest like code distance where you're like, oh, just how long would it take me to walk? Yeah. Any questions? How's your thumb? Thumbs up, thumbs down, sideways. Okay, yeah. Just know that basically, I think the next one's going to be a lot easier to understand. Like, okay, you're basically just seeing how far these points are. So the next one is Euclidean distance, which is just basically like the good old Pythagorean theorem. A squared plus b squared equals c squared. I remember that like in high school probably, right? Like this is kind of like the classic, like how far something is. And this is actually the distance of like how far the crow flies. You'll notice that basically there's, instead of using absolute value, we actually use squared. So you can see that it's squared here, and then we take the square root of it, and that will give us the distance. And so again, it's kind of like in this case, we're kind of adding them up all together and then taking that square root. So if you were to code this, what this will look like essentially the same exact points, 2, 1, 3, or sorry, 2, 3, 5, 1, minus 1, 3. You can see here, basically, we take a difference between these two parts, this x1 minus x2. So if I run this now, this will basically give me a 1, 4, 2. I square each part. I just square each of those distances. So this will be 1, 16, 4. Okay, and then all I got to do is add them together. So you can see it's going to be 21. And then take the square root of that. And that gives me about 4.58. So note that this is a smaller distance than the original 7, even though it's the same points. And that kind of hopefully makes sense that if you walk the block, it's going to take a lot longer for you to get somewhere versus just going straight across. And that's what the Pythagorean, or what do I call it? I don't even remember what I call it now. Euclidean distance. The Euclidean distance is basically going from cutting across right over versus like walking over. And you can do this as many times you want in as many dimensions you want. So if you have, 3 dimensions, you now have like some point in space. So before, if you had like this point here, hopefully this kind of makes sense. But if I had a point right here and a point over here, I could say, okay, go off in this direction, going up and then going in. And you say, oh, that's my point right here, versus just going straight forward. So that's kind of like what's going on in 3D. And that's what this is implementing. But you could do this as many times as you want in 4D, because all you have to do, either for Manhattan or for Euclidean, is basically just finding these differences between this first coordinate, the second coordinate, and the third coordinate. And then for Manhattan, you can just basically just take the absolute value and add them all up together. Pretty simple. For Euclidean distance, you square them first, and then you add them up together. And then to undo that square root, or square, you do take the square root of it. Okay, so just another way to calculate distance. Last one is Minkowski distance, which is basically, it's kind of the same idea. Is essentially you have, you take it to the power. So essentially you're going to take the difference between that, raise it to a certain power, and then just take that root power of it. So if I raise it to the power of 3, I would divide it by the power, or I raise it to the power of 1/3. If I raise it to the power of 4, divide it by 1/4. So what this will essentially do is will lessen the distance smaller and smaller. It'll make more extreme values less extreme. So we can see what this kind of looks like. I just made a Minkowski, and basically Euclidean and Manhattan are the same things, except your C here is either the power of 1 or the power of 2. So you can see here, I just wrote a little quick thing. Basically, I take the absolute value, I take the difference between those 2 points. So remember these 2 points right here. Basically, I take the difference between 2 and 1, 3 and minus 1, 5 and 3. Take the difference between that. I raise each one to the power of whatever I call it, right? So if I raise the power of 2, power of 3, power of 10, doesn't really matter. This will basically get a new thing where each of those distances are now raised to the power. I add them up to all together, and then I basically undo that power by doing it raised to the power of 1 over C, whatever that C is. And so we can basically do whatever we want in this case. So for example, if I wanted to do a Minkowski of the power of 2, we saw that was like about 4.5, I think. So you can see here, if I did the power of 1, it'd be 7, because that was basically the Manhattan distance. If you imagine we do the power of 10, you can see it gets smaller and smaller. If I do like 100, I don't even know if this will work. there. You can start seeing one is basically, it's like, oh, really, really small. And you could basically like kind of keep going through. Usually the Minkowski distance is when like you want to punish like more extreme values and stuff like this to make it closer together. So maybe you want something that's technically further away, but you know, you want it to be considered closer together. It's just another way of doing things. Another distance I didn't have on here, which can be used for k-nearest neighbors, is a cosine distance. And that's got some extra features in there, but I'll leave that for the curriculum if you want to go into that stuff. But so just basically, there's just another metric for you to measure how close something is. You normally wouldn't be writing this whole thing out. Usually you would just be describing, like you would just basically be passing in the algorithm, which distance metric should you use? Okay. Thumbs up, thumbs down, sideways. How you feeling? Tell me, Alan, what's the thing that's kind of making you feel a little, not sure? I can unmute you if you. Oh.
Okay. Yeah, the formulas are just, I understand the principle, but then when it comes to the formulas, it's just like.
Yeah, the formulas are more like formalizing what's going on. Formalizing, right? That's really what's going on. It's just making it more mathematical so it's easier to like code it. But in reality, it's like, oh, you're just seeing how far the distance is. It's easy. It's relatively easy when you're like using Euclidean and Manhattan. You're like, okay, I understand that. When you go into like higher Minkowskis, it's a little bit more abstract. But hopefully you kind of see like why we can use that. We're like, oh, we had this Manhattan distance where we're just walking along the blocks. Euclidean distance where we're walking across directly. Minkowski distances are a little harder to wrap your head around. It's like, what exactly is going on? But they're another way for us to measure distance. Usually we'll use Euclidean if we're doing distance in this way. The other more common one is cosine distance, which basically it's another just way of calculating how close something is. Okay. But part now it's like we can figure out how close things are. Yay. So that leads us into the actual algorithm. And again, we don't actually have to write all that stuff down for most of the time to do this. So like I said, k-nearest neighbor is a classification. It should be an unsupervised version. Did I put supervised? Is that right? Wait a second. No, this should be unsupervised. You're wrong. Ask Victor doesn't know what he's talking about. Now I'm all messed up. No, this is unsupervised. Okay. Unless I'm mixing that. No. Okay. So basically what it is that you have, oh no, it is supervised. Oh, I'm sorry. I messed up. Forget what other past Victor said. It is a supervised learning algorithm. Dang it, Victor. So it's a supervised learning algorithm because we're using our other neighbors to begin with to figure out what our last one is. I'm sorry, I messed up before. I was thinking of another algorithm in my head. It might be a little late in the day for me. It's not really not that late, but it feels late. But basically what happens is we have our different groups. For example, this is like class A and class B. This is a diagram I found was really useful in mine that kind of shows this. Basically, you have like those like the bunch of blue squares and these red triangles, and our green point is our test point. And you say, okay, who like green point, who do you belong to? Do you belong to the green squares or the blue squares or the red triangles? Which one is it? And basically we say, well, who are you closest to? Depending, if you're closer to, like literally physically closer to the red triangles, you're likely a red triangle. If you're closer to the blue squares, you're a blue square. So this has a good example of what is going on. First, you basically have all the points plotted out, essentially, mathematically, right? And you have like, for example, these stars and these triangles. And this new sample point goes like, I don't know, which group am I supposed to be into? And basically after this point, okay, well, we have class A and class B. And we say, all right, the stars over here say, okay, I am this far away from this point. And all the green triangles, well, I'm this far away overall from the green point. And you say, okay, who should you belong to? Who is closest to you? And you say, okay, whoever you're closest to, that's what you're gonna be. And this is where essentially I kind of imagine like in my little play head of like what this looks like if I like personify all of these little data points is you can imagine like the, what's it called? Those triangles are all like a community. And they're like, if you're closer, they're trying to grab you to bring you closer to their group. And then the the stars, if they're closer, they're trying to pull you to their group. And whoever's closest is going to overall win. So you might have one person who's really close to you, but you might have like 3 stars that are a little bit further away, but there are 3 of them that are all pulling you towards that point. So it's kind of a balance between that two. And basically you just want to average them all together. Yeah, this is from a data camp, which I thought was a good example of what's going on. But it's actually relatively simple then to actually perform the algorithm. Essentially you have as all the data points already classified, like so you already know what those stars are, what those green triangles are, and then you put in your new data point and you say, okay, who's closest overall? And you basically use that metric, and then whoever's closest, that's that thing. So if you say the triangles are closer, you're now a triangle. And this is where the K part comes in, the K nearest neighbors. You only pull in that K number of neighbors that are close by. So you say, who are my 3, if you did K equals 3, like in this diagram, who are my 3 nearest neighbors? Well, okay, in this case, you can see that basically this triangle, and this star are the 3 closest neighbors. So then you would calculate it from there and say, well, who's the closest, or what's the most, which one is actually going to be it? And then, so this, sorry, I'm missing out my words right now. This triangle basically is like, you basically have a vote. It's like, okay, well, these are the 3 nearest neighbors. Which one's more? Is there more triangles or more stars? Well, there's more triangles in this case. So this will also be a triangle. Okay, but it only matters for those nearest neighbors going on. So you kind of imagine it's like, even though, you might have more of them, if you're closer to begin with, you're going to have a higher vote in that sense. But if you have just one triangle that's really close, but then there's like other stars that are a little bit further away, but there's more of them that are overall closer, the stars will win in that case. So it all depends exactly which going through. So it actually does a pretty good job. So really nice advantages of this is that it's super easy to like make it learn. There's no training phase. The training is the data itself. You don't have to like go through a whole process of training it and what's it called? Iterating over and over like a decision tree or any other machine learning algorithm. So it's super easy to implement. And it's also easy to interpret. Basically, it's like if you're closer, like if the 3 nearest neighbors or K number neighbors are closer to you, like if there's more one class that's closer to you, then you're that class. It's pretty easy for you to interpret that way and say, okay, that's why this person or this, sample, this data point is this class because there are just more people that are closer to them, okay? Now there are some disadvantages. So one disadvantage is that all of this data, this training data, so these triangles and these triangles and stars that already exist have to be kept in memory. So basically it means that if you have a large amount of data, it can be a huge amount of your data because there's no way to basically compress that really information down because you have to know where each point is. So if you have a large amount of data, it can be a huge thing. It's not robust since it doesn't generalize well. So if you have a new, like for example, if you have a data point that's right over here that really you've never seen before, like there's no one over here, you don't know if in this corner, if it should be a star or a triangle. We can say the algorithm can give you an answer, but does it really make sense for you to include it with one of these groups? It might not really. There are also like soft boundaries that can be troublesome. So the problem is like, for example, if there's a lot of mixing, so right now you can see there's a very clear boundary between the triangles and the stars, but if there's some bleeding over from triangles and bleeding over from stars on each side, so they're kind of blending, a soft boundary, it's a little bit harder to say, well, what's gonna be this thing? It might go back and forth a little bit, and that might not be the best way. You can also do some weird stuff where you can kind of have the data point kind of sneak in from the side a little bit, where it's like, it doesn't really make sense for it to be pointed there. So sometimes these boundaries can give a huge issue. But if it's within a big group, it's a lot easier. It's on that edge, it's a lot harder to figure out exactly when there's a lot of mixing. And then the last one is this thing called the curse of dimensionality, which you'll hear a lot of. Basically, it's that as you have higher and higher dimensions, it's actually really easy to have things that are isolated by itself. So as you increase the dimension, it actually makes it really difficult to know or have things that are close by. Things tend to be more separated out in higher dimensions. You can fix this a little bit with PCA. So PCA can help kind of like alleviate some of this like what's closer and stuff like that. Kind of lowers it down into a lower dimension and kind of reduces that dimensionality. Other parts is using high dimension. So instead of using the cosine dimension similarity, uses angles essentially. And instead of using the actual distance directly from it, it uses essentially what direction you're in. And so this can be a fix for high dimension. So you'll see cosine similarity really used often for k nearest neighbors for this kind of like machine learning algorithm. Okay, so those are the advantages, disadvantages. Again, it's really easy to implement. It's really easy to interpret, but it has to be kept in memory. It's not robust. It's got some extra parts in there. So it's not the best one here. The hardest part too is, or not one of the hardest parts is determining, okay, how many neighbors do you actually consider? And this is actually when you basically start off, you might need to start with different numbers and kind of play around with what's going on. You actually, usually this algorithm goes, is you, to figure out what the best K is, you basically have some training style, you have them training, and then you test out with things that you already know and see how well K actually performs and see how well those actually get matched in the right spot. So you can see that K is a big aspect of like, what should K be? It's not super clear because if you make K too big, you're including too many people that are really far away. And this leads into like overfitting and underfitting. So basically what you want to do is you test out different Ks and you say, well, okay, let's see what happens. Is if you have, you know, two, like, let's say two simple, you're underfitting, for example, if you're looking at just, what's it called? Like if you use many neighbors, well, it's really hard to figure out exactly what's going on here. If you use too few neighbors, you might get more overfitting where it's basically forcing it to be a specific part. So you see these like really jagged lines where basically you're only putting in if you're really close to here. So there's a balance between how many Ks. The best thing to do is essentially do an elbow plot. So this is where you have your training, well, I guess it's your training, but basically you have your validation plot and your training plot and see how much accuracy you have on each part. And this is with actually like part of the data is already, you know what the values are, you know what the classification is. And you would basically pick where you get this just right, where it's just about there. And that's where your K would be. And usually that K is between 1 and 20. It's usually not higher than 20. Okay. And then the last part, just to implement it, you can see here, this is directly from the K nearest neighbors classifier. Again, we're just importing these parts here and I'm actually visualizing it. So if I plot this out, and I'm just running this through because we're a little low on time, but you can check it out on the notebook for sure. But basically know that I have different data points right here and it's gonna be in 3 dimensions. So I have, this is essentially my prediction points, my, what's it called? My training data, and these are the different classes. Okay, and then I'm actually gonna go ahead and say, okay, oh, I have some new data points. Okay, what should it look like? So you can see here is that this is kind of what K nearest neighbors are. So I believe the big circles are the my points I'm testing out. So you can see here is that most of these are this class right here. These are orange right here. These are red. You can see right here, this is orange, even though it's pretty far away. So that's where it's like kind of hard to tell, like with Christmas dimensionality, where like things get really kind of separated out. But you can see for the most part, it's a pretty good job of finding these big circles for where they should be. And this all depends on what kind of metric you use. In this case, I think I used Euclidean. I don't know if I use Euclidean. Yeah, I used Euclidean here. So you can change a different metric here. You can change it to Minkowski, or you can change it to, what's it called? I'm messing up the name, Manhattan distance. So you can basically have different parts in here. So if I got rid of this metric right here, this might actually make a difference. I don't know if it actually makes a difference in this case. So yeah, so it makes the same decisions, but you would actually adjust those parts. Okay. So yeah, that's kind of K nearest neighbors. It's relatively like easy. Like the metric distance is kind of like a confusing part. We're like how are we measuring this? But the point is basically if they're close together, or you look at the first K and K nearest neighbors. So if you have 3 nearest neighbors, you look at the 3 most nearest neighbors and say, what are they? Are they red? Are they orange? Are they gray? And then you say, okay, based on that, that's what you are. So yeah, relatively simple one. Okay, cool. Any questions you have, Alan? All right, cool. So I'll go ahead and stop here.